What if time wasn't the steady, unchanging force we've always believed it to be? Picture an astronaut floating in space, watching years pass by on Earth in what feels like mere months, or standing at the edge of a black hole where seconds stretch into eternity. This isn't the plot of a sci-fi blockbuster. It's the astonishing reality of time dilation, one of the most profound and overlooked consequences of theory of relativity. For over a century, scientists have wrestled with the implications of a universe where time is fluid, where gravity and motion twist the very fabric of existence into something unrecognizable. And yet, so much of this story remains untold. Today, we're peeling back the layers of one of physics' greatest mysteries to reveal 24 forgotten predictions about time dilation. Ideas so radical, they'll make you question everything you thought you knew about the flow of time. From the bizarre ways time behaves near cosmic giants like neutron stars to the eerie experiments that prove clocks tick slower on a speeding airplane, we're diving into the hidden corners of temporal physics. These aren't just abstract theories, they're real phenomena with consequences that could reshape our understanding of reality itself. Imagine a future where interstellar travelers return to find their loved ones decades older, or where black holes serve as gateways to time loops beyond our wildest imagination. The universe is stranger than fiction, and the secrets of time dilation are at the heart of it all. But why does this matter to you? Because time isn't just something we measure, it's the invisible thread weaving through every moment of our lives. What if the key to unlocking the cosmos' greatest mysteries lies in understanding how time bends, warps, and fractures under extreme conditions? From first sparks of insight to the cutting-edge research pushing the boundaries of physics today, this journey will take you to the edge of human knowledge and beyond. So buckle up, we're about to explore the untold consequences of relativity, where the rules of time as we know them no longer apply, and the universe reveals its most astonishing secrets. One of the most mind-bending demonstrations of time dilation is the famous twin paradox, a thought experiment that feels ripped straight from science fiction, yet is grounded in the unshakable laws of physics. Imagine two identical twins. One stays on Earth while the other boards a spacecraft traveling at nearly the speed of light. When the traveling twin returns after what feels like a few years, they step out of the ship to find their Earth-bound sibling has aged decades. This isn't a trick of perception, it's the universe enforcing relativity's strict rules. Time literally passes slower for the twin in motion, compressing their experience of years into what Earth observes as mere moments. But how does this actually work? The key lies in its realization that time and space are into a single fabric, one that bends and stretches depending on gravity and velocity. The faster you move, the more time slows down relative to someone standing still. For the twin racing through space at close to light speed, their clock ticks slower compared to the twin on Earth. It's not just about speed, though. Acceleration plays a crucial role too. When the traveling twin turns around to come home, their change in direction further twists time's behavior, locking in the age difference. This paradox forces us to abandon the idea of absolute time and accept that the flow of time is deeply personal, shaped entirely by your own motion. What's truly astonishing is that we've measured this effect in real life, not with twins, but with ultra-precise atomic clocks. Scientists have placed clocks on airplanes, rockets, and even the International Space Station, only to find they tick measurably slower than their Earth-bound counterparts. The same physics that creates the twin paradox also affects everyday technology. GPS satellites orbiting high above Earth at thousands of miles per hour experience time dilation strong enough to throw off their timing by microseconds every day. If engineers didn't account for this, your navigation apps would misplace you by miles within minutes. Relativity isn't just some abstract theory, it's quietly shaping the modern world in ways most people never realize. So what does this mean for the future? If humans ever achieve interstellar travel at relativistic speeds, time dilation could turn into both a blessing and a curse. A voyage to a star 100 light-years away might take only a decade for the crew, but back on Earth, centuries could pass. The implications are staggering. Explorers might return to a world unrecognizable, where everyone they knew is gone. This isn't just speculative, it's an inevitable consequence of the universe's deepest laws. The twin paradox forces us to confront the unsettling truth that time isn't just a backdrop to our lives. It's a malleable, ever-shifting dimension that bends to the whims of motion and gravity. And if that doesn't make you question everything, just wait. We're only getting started. Now, let's turn our attention to one of the most extreme environments in the universe, the edge of a black hole. Here, gravity isn't just strong, it warps the fabric of space and time so drastically that the laws of physics as we know them begin to unravel. Picture a spaceship creeping toward a black hole's event horizon, the point of no return. To an outside observer watching from a safe distance, something bizarre happens. The ship appears to slow down, then freeze in place as if time itself has stopped. The closer it gets to that invisible boundary, the more time stretches, distorting seconds into hours, minutes into years. This isn't an illusion. It's the universe enforcing one of relativity's most dramatic predictions. What's actually happening here? Theory tells us that gravity doesn't just pull on objects, it bends time. The stronger the gravitational field, the slower time moves relative to weaker fields. Near a black hole, where gravity is crushing enough to trap light, time dilation becomes so extreme that a single minute for someone near the event horizon could equate to centuries passing elsewhere in the universe. Imagine a star collapsing into a black hole. From our vantage point, its final moments would appear to stretch infinitely, as if the star is frozen in its death throes, never quite vanishing from view. This eerie phenomenon, known as gravitational time freezing, means black holes don't just consume matter, they distort our very perception of time's passage. But what would this mean for an astronaut brave or reckless enough to approach a black hole's edge? For them, time would feel normal. Their watch would tick steadily, their heartbeat unchanged. But if they could look outward, the universe would appear to speed up in a dizzying blur. Galaxies might age before their eyes, civilizations rising and falling in what feels like moments. The cruel irony. While they'd experience only a brief journey, anyone waiting for them back home would have long since perished, lost to that raced by in their absence. This isn't just theoretical. It's a harsh reality future explorers would face if we ever develop the technology to venture near these cosmic monsters. Here, where things get even stranger. If time grinds to a halt at the event horizon, does that mean black holes are cosmic time capsules, preserving moments forever in their gravitational grip? Some physicists argue that from our perspective, an object falling in never truly crosses the horizon. It just fades into an infinite, eternally suspended in time. Others suggest quantum effects might eventually break this illusion, but the debate remains unresolved. What's certain is that black holes don't just challenge our understanding of space. They force us to confront the unsettling fluidity of time itself. The implications ripple far beyond thought experiments. If humanity ever harnesses the energy of black holes, perhaps as gravitational anchors for faster-than-light travel, we'd need to account for time dilation's steep toll. A mission near a black hole could strand travelers in a future unrecognizable to them, severing ties with everyone they once knew. And yet, this very distortion might hold the key to probing the universe's deepest mysteries. By studying how black holes warp time, we inch closer to answering existential questions. Is time truly fundamental, or just an emergent property of a deeper cosmic code? The answers could rewrite physics and our place in the cosmos, forever. You might think time dilation is something that only happens in the far reaches of space or in extreme experiments. But here's the astonishing truth. Earth's own gravity bends time enough for us to measure it right here at home. Take two identical atomic clocks, place one at sea level and another on the peak of Mount Everest, and over time they'll drift out of sync. The clock on the mountain will tick ever so slightly faster, gaining a tiny fraction of a second compared to its counterpart below. This isn't a glitch, it's gravitational time dilation in action, proving that even our planet's gentle pull warps the flow of time in ways we can actually observe. Why does this happen? Its equations reveal that gravity doesn't just pull objects downward, it stretches time itself. The closer you are to a massive object like Earth, the stronger gravity's grip and the slower time moves. At sea level, where gravity is strongest, time drags just a bit compared to higher altitudes where the planet's pull weakens. The difference is minuscule, we're talking nanoseconds over years, but it's real. This effect was confirmed in a groundbreaking experiment in the 1970s, when scientists flew atomic clocks on airplanes and compared them to clocks on the ground. The results matched Relativity's predictions perfectly. Time really does pass faster the farther you are from Earth's core. Here, where it gets even more fascinating. This subtle time warp isn't just a curiosity, it's something engineers have to account for in everyday technology. GPS satellites orbit about 12,000 miles above Earth, where gravity is weaker than on the surface. Without correcting for the faster ticking clocks, GPS calculations would be off by nearly 7 miles per day, rendering navigation systems useless. Relativity isn't just a theory studied in labs. It's quietly embedded in the devices we use every single day. But what does this mean for us? Imagine living your entire life at the base of a mountain while your twin resides at the summit. Over decades, the mountain-dwelling twin would age a tiny bit faster, not enough to notice in a lifetime, but enough for precision instruments to detect. It's a humbling reminder that time isn't a universal constant, it's a fluid experience, shaped by where you stand in the universe. And if Earth's modest gravity can bend time, imagine the distortions near denser objects like neutron stars, where the difference isn't nanoseconds, but years. This prediction isn't just about clocks on mountains. It's a window into the hidden flexibility of reality itself. One of the most striking confirmations of time dilation happens not in deep space, but inside massive machines here on Earth, particle accelerators. Take muons, unstable subatomic particles that typically vanish in just 2.2 microseconds. Left to their own devices, these particles decay almost instantly, like cosmic fireflies blinking out of existence. But when scientists hurl them through accelerators at 99.9% the speed of light, something extraordinary happens. The muons cheat death, surviving up to 30 times longer than they should. This isn't magic, it's relativity in action, stretching time itself to keep these particles alive far beyond their natural expiration date. How does this work? Theory tells us that time slows down for objects moving close to light speed. From our perspective in the lab, the muon's internal clock ticks slower, stretching its fleeting lifetime into something measurable. But here's the twist. From the muon's point of view, it's not moving at all. It's the rest of the universe rushing past at near light speed. In its own frame of reference, the muon still decays in 2.2 microseconds. The difference lies in the fact that distances contract at such high velocities, allowing the muon to traverse the accelerator's length before it has time to disintegrate. This mind-bending symmetry is the heart of relativity. Both perspectives are equally valid, yet each tells a radically different story about time's passage. This phenomenon isn't just a curiosity, it's a cornerstone of modern physics. Particle accelerators like CERN rely on time dilation to study particles that would otherwise vanish before scientists could observe them. Without relativity's time-stretching effect, high-energy collisions would be over in an instant, leaving no trace of the exotic particles they produce. Instead, time dilation gives researchers a precious window into the quantum realm, revealing secrets about antimatter, dark matter, and the fundamental forces holding the universe together. But the implications go even deeper. Muons raining down from Earth's upper atmosphere, cosmic rays accelerated by distant supernovae, also outlive their expected, proving time dilation isn't confined to labs. These natural particle beams travel so fast that they reach the ground despite their fleeting existence, offering independent proof of predictions. It's a humbling reminder that the laws governing subatomic particles and accelerators are the same laws governing the cosmos itself. What does this mean for the future? As we push particles closer to light speed in next-generation colliders, time dilation effects will become even more extreme. Some theorists speculate we might even uncover particles that appear frozen in time, their decay delayed indefinitely by relativistic speeds. Whether that's possible remains to be seen, but one thing is certain. The muon's defiance of decay isn't just a laboratory trick. It's a glimpse into the universe's hidden clockwork, where time bends to the whims of velocity and the impossible becomes routine. In 1971, two physicists named Joseph and Richard decided to put theories to the ultimate test, not in a lab, but in the skies. They took 4 ultra-precise atomic clocks, placed them aboard commercial airplanes, and sent them flying around the world in opposite directions. When the clocks returned and were compared to identical clocks left stationary on the ground, something extraordinary emerged. The traveling clocks had lost time. Not much, just a few hundred nanoseconds, but the discrepancy was undeniable. Time had literally slowed down for the clocks in motion, just as relativity predicted. This wasn't a minor academic curiosity. It was the first real-world validation that time dilation wasn't just a mathematical quirk. It was woven into the fabric of reality itself. What made this experiment so groundbreaking? And weren't just testing speed's effect on time, they were also measuring gravity's role. The eastbound plane, flying with Earth's rotation, moved faster relative to the ground, causing its clocks to tick slower due to velocity-based time dilation. But the westbound plane, flying against the rotation, moved slower, so its clocks actually ticked faster than the ground clocks because they experienced slightly weaker gravity at higher altitudes. The results were a delicate dance between two competing effects, velocity slowing time down and reduced gravity speeding it up. The numbers matched equations to a stunning degree, silencing skeptics who dismissed time dilation as theoretical fantasy. The implications ripple far beyond a single experiment. Modern technologies like GPS rely on these very principles to function accurately. Without accounting for the time differences between satellites in orbit and receivers on Earth, navigation systems would fail within minutes. But the experiment did something even more profound. It made relativity tangible. For the first time, people could point to a real, measurable phenomenon and say, this proves time isn't fixed. It transforms abstract equations into something you could hold in your hand, or at least, something you could fly around the world in a suitcase. Here, where it gets even more fascinating. The experiment also revealed a hidden truth about our planet. Earth itself is a time machine. Every time you climb a flight of stairs or board a plane, you're altering your own experience of time, however imperceptibly. The faster you move, the more time slows down. The higher you go, the more it speeds up. These effects cancel out for most daily activities, but they're always there, humming in the background of existence. And didn't just confirm a century-old theory. They showed us that time dilation isn't confined to black holes or particle accelerators. It's happening right here, right now, in the skies above us and the ground beneath our feet. So what does this mean for the future? As humanity pushes toward faster air travel, perhaps even hypersonic jets or suborbital flights, time dilation will become more than a scientific footnote. Passengers on these vehicles might age microseconds less than those on the ground, a tiny but inevitable consequence of relativity. It's a reminder that even as we conquer new frontiers, we're still bound by the universe's deepest laws. The experiment wasn't just a triumph of physics. It was a wake-up call, revealing that time, the most familiar part of our lives, is far stranger than we ever imagined. And the closer we look, the more its secrets unravel. Every time you use your phone to navigate, you're relying on one of the most practical applications of time dilation, a system that would fail spectacularly without corrections. GPS satellites orbit Earth at roughly 8,700 miles per hour, high enough that gravity's grip is weaker than on the surface. Both their blistering speed and their altitude twist time in opposite directions. Velocity slows their clocks down, while reduced gravity speeds them up. Left uncorrected, these competing effects would throw off GPS timing by about 38 microseconds per day. That might sound negligible, but in the world of navigation, where light travels nearly 300,000 kilometers per second, even microseconds matter. Without relativity's adjustments, GPS coordinates would drift by over 6 miles daily, turning your road trip into a cross-country odyssey of wrong turns. So how do engineers solve this cosmic conundrum? Each GPS satellite carries an atomic clock pre-programmed to tick slightly faster than its Earth-bound counterparts, a deliberate tweak that cancels out time dilation's distortions. Before launch, these clocks are set to run about 45 microseconds per day faster, accounting for the slower ticking they'll experience in orbit. It's a brilliant balancing act. The speed-induced slowdown and gravity-induced speed-up almost cancel each other out, but not quite. The remaining discrepancy, about 7 microseconds daily, is meticulously calculated and corrected in real time by ground stations. This isn't just precision engineering, it's humanity bending the universe's rules to make modern life possible. The stakes couldn't be higher. Airplanes guiding themselves through fog, emergency responders racing to accidents, even farmers planting crops with pinpoint accuracy, all depend on GPS staying ruthlessly accurate. But here's what's truly mind-blowing. This system wasn't designed by physicists chasing abstract theories. It was built by engineers solving a very real problem, proving that relativity isn't confined to textbooks. The equations scribbled in the early 20th century now live in every smartphone, quietly correcting for time warps most users will never know exist. Yet this solution reveals a deeper truth about our universe. Time dilation isn't some exotic effect limited to black holes or particle accelerators. It's woven into the infrastructure of daily life. Those 32 satellites whizzing overhead aren't just navigation tools. They're constant reminders that time is fluid, and gravity's fingerprints are everywhere. The next time your map app guides you flawlessly through an unfamiliar city, remember, you're not just seeing technology at work. You're witnessing humanity outsmarting the universe itself, one corrected nanosecond at a time. But the story doesn't end there. As we push satellite technology further, with next-generation systems like Europe's Galileo or China's, relativity's corrections must become even more precise. Some proposed megaconstellations might orbit higher or faster, demanding new calculations to keep time dilation in check. And if we ever deploy satellites around other worlds like Mars or Jupiter, their wildly different gravities will require entirely fresh equations. GPS isn't just a triumph of engineering. It's a blueprint for how humanity will navigate the cosmos, armed with the knowledge that time is never quite what it seems. Hollywood loves bending the rules of physics for dramatic effect, but when it comes to time dilation, some films get eerily close to reality. Take Interstellar, the scene where astronauts land on Miller's planet, orbiting a supermassive black hole, only to return to their ship and find there has aged 23 years. It's a jaw-dropping moment, but here's the twist. The science behind it is surprisingly sound. The film's scientific consultant, physicist Kip, worked tirelessly to ensure the portrayal of Gargantua, the fictional black hole, matched its equations. The result? A depiction of time dilation so accurate it spawned peer-reviewed papers. But how does Interstellar's vision hold up under scrutiny? The key lies in the planet's proximity to Gargantua's event horizon, where gravity is strong enough to stretch minutes into years. In reality, a planet that close to a black hole would be torn apart by tidal forces. But the film cleverly sidesteps this by placing Miller's planet just far enough to survive while still experiencing extreme time dilation. The math checks out. Time slows dramatically in intense gravitational fields, meaning every hour on the surface really would equate to years passing elsewhere. It's a rare case where Hollywood's spectacle aligns with scientific possibility, even if the scenario itself is engineered for storytelling. Not all sci-fi gets it right, though. In Avengers: Endgame, the Hulk claims time works differently in the quantum realm, allowing the heroes to time travel by manipulating time vortices. It's a fun plot device, but it bears little resemblance to actual physics. Real-time dilation depends on gravity or velocity, not mysterious realms with flexible rules. Even Star Trek, with its warp drives and subspace anomalies, often treats time as a narrative tool rather than a relativistic consequence. The difference: Interstellar starts with science and builds its fiction around it, while most franchises start with fiction and sprinkle in science as an afterthought. What makes Interstellar stand out isn't just its accuracy, it's how it uses time dilation to explore human stakes. The heart-wrenching scene where Cooper watches decades of missed messages from his children isn't just drama, it's a visceral illustration of Relativity's emotional toll. This is where science fiction shines, not just in depicting the how of time dilation, but the what if. What if you returned from a voyage to find everyone you loved had moved on without you? That question lingers long after the credits roll, bridging the gap between equations and empathy. Yet even Interstellar takes creative liberties. The sequence where Cooper navigates a fifth-dimensional space to communicate with his daughter veers into speculative territory. While the film grounds its time dilation in real physics, it's unafraid to venture beyond known science when the story demands it, and that's okay. The best sci-fi strikes a balance, using real principles as a springboard, not a straitjacket. After all, if movies stuck rigidly to textbook physics, we'd lose the wonder that makes them so compelling. The takeaway: while most films treat time dilation as a narrative shortcut, a handful, like Interstellar, remind us that reality can be just as thrilling as fantasy. The next time you watch a character leap through time, ask yourself, is this science or just storytelling? Sometimes the answer might surprise you. Deep in the cosmos, nature has been running its own time dilation experiments for billions of years, and the evidence rains down on us daily in the form of cosmic rays. These high-energy particles, often protons or atomic nuclei accelerated to nearly light speed by supernovae and black holes, carry a fascinating secret. From our perspective on Earth, their internal clocks tick far slower than ours. A particle that should decay in microseconds might survive for centuries of our time, stretched across interstellar space like a rubber band pulled taut by relativity. These aren't just random space travelers. They're natural test subjects proving right with every impact on our atmosphere. Consider the journey of a single cosmic ray proton, ejected from a dying star millions of light years away. At rest, it would decay into other particles almost immediately. But hurtling through space at 99.999% the speed of light, time for that proton slows to a crawl. What feels like a brief trip from its perspective becomes an epic voyage lasting from hours. By the time it collides with Earth's upper atmosphere, creating a shower of secondary particles we can detect, it's essentially a time traveler, carrying the imprint of its relativistic journey in its extended. This isn't theoretical. Detectors like the Pier Auger Observatory in Argentina routinely catch these time-stretched particles, offering real-world confirmation of Relativity's predictions. The implications are staggering. Cosmic rays serve as a universal laboratory, demonstrating time dilation on scales no human-built accelerator could match. Some of these particles pack energies so extreme, millions of times more powerful than anything produced at CERN, that their time distortion effects are correspondingly dramatic. A muon created in a cosmic ray shower might reach the ground despite having a natural lifetime too short to traverse even a fraction of Earth's atmosphere. From the muon's perspective, it lives its usual 2.2 microseconds, but Earth's atmosphere appears length contracted, allowing the journey to fit its brief existence. From our viewpoint, the muon's clock runs slow, giving it enough time to survive the descent. Both explanations are equally valid, showcasing relativity's beautiful symmetry. What's truly humbling is realizing how much of our understanding of particle physics relies on these natural relativistic effects. Without time dilation, cosmic rays would never reach Earth's surface in detectable numbers, leaving us blind to high-energy processes across the galaxy. Pioneering physicists discovered this in the 1930s when they compared muon counts at mountain peaks versus sea level, finding far more survived the longer descent than classical physics allowed. Their work laid the foundation for modern particle physics and proved that the universe itself runs on relativistic time. But cosmic rays don't just teach us about physics, they reveal our place in a dynamic, time-bending universe. Every minute, about 100 of these time-dilated particles pass through your body, relics of distant cataclysms that occurred long before Earth formed. Some may have been accelerated by the same supernova shockwaves that seeded our solar system with heavy elements, making them not just messengers of relativity, but literal pieces of our cosmic ancestry. The next time you feel a sunbeam, remember, you're also being bathed in particles that have cheated time itself to reach you, stretching the boundaries of existence to deliver their ancient stories. Time dilation isn't just a local phenomenon. It might hold the key to understanding the universe's ultimate fate. Picture a cosmos where expansion accelerates so dramatically that distant galaxies recede faster than light, their light never reaching us again. In this scenario, time itself could stretch into near-infinite slowness at the edges of the observable universe, creating pockets of space-time where the universe's final moments play out in frozen eternity. This isn't science fiction. It's a real possibility grounded in the interplay between relativity and dark energy, the mysterious force driving cosmic acceleration. The connection between time dilation and the universe's expansion hinges on field equations, which link the geometry of spacetime to the energy within it. As dark energy pushes galaxies apart, the stretching of space also stretches time, especially for objects caught in regions of rapid expansion. Imagine two civilizations separated by billions of light years, one in a galaxy tethered to a supercluster, the other adrift in a void where expansion dominates. For the isolated civilization, time would appear to crawl compared to their counterparts in denser regions. The farther apart regions drift, the more their clocks desynchronize, not just from motion or gravity, but from the fabric of spacetime itself being pulled taut. Some cosmologists take this idea even further. In models where dark energy's strength increases over time, a scenario called the Big Rip, the universe could tear itself apart, with expansion overwhelming even atomic bonds. Here, time dilation would become grotesquely extreme. In the final moments before complete disintegration, clocks in different regions would tick at wildly different rates, as if the universe were a shattered mirror reflecting fractured timelines. Observers in one region might witness the cosmos ending in a flash, while others experience it as an endless, slow-motion unraveling. But there's a twist. If expansion continues indefinitely, the universe could enter a state of heat death, where matter is so dispersed that time loses all meaning. In this cold, dark future, pockets of isolated particles might experience time so dilated that a single second for them could equate to trillions of years elsewhere. The very concept of now would fracture, with no shared reference point to synchronize events across the void. This raises a profound question. If time flows at radically different rates across the cosmos, can we even speak of a unified cosmic timeline? The implications ripple through modern astronomy. When we observe distant supernovae to measure cosmic expansion, we're also glimpsing time dilation's cumulative effects. Light from these explosions arrives stretched, not just from the effect, but because time itself passed slower in the universe's denser, younger eras. This subtle signal, buried in the light of ancient stars, helps astronomers map how dark energy has warped spacetime over billions of years. What does this mean for our place in the universe? If time dilation is woven into the cosmos's expansion, then the farther we peer into space, the more we're looking into a past where time flowed differently. The atoms in our bodies, forged in primordial stars, carry memories of a universe where seconds ticked slower, a relic of when gravity's grip was and spacetime less stretched. Far from being passive observers, we're participants in a grand temporal tapestry, our very existence shaped by the universe's uneven clock. And as the cosmos accelerates toward its unknown fate, time dilation may be the silent force scripting its final act. At the smallest scales of the universe, where particles blink in and out of existence, and gravity becomes a fuzzy, uncertain force, time itself may break all the rules we thought we knew. This is the frontier of quantum time dilation, a realm where relativity collides with the bizarre unpredictability of quantum mechanics. Picture an electron orbiting an atom's nucleus. According to quantum theory, it exists in a cloud of probabilities rather than a fixed path. Now imagine that this electron's experience of time fluctuates just as unpredictably, speeding up or slowing down in ways that defy classical physics. This isn't science fiction. It's a radical prediction emerging from laboratories pushing the boundaries of quantum gravity research. The key to this mystery lies in the unresolved conflict between general relativity and quantum mechanics. Relativity treats time as a smooth, continuous fabric, while quantum theory insists everything, including gravity, comes in discrete, jittery packets. When you try to apply both frameworks simultaneously, as you must near black holes or in the early universe, the math breaks down catastrophically. But recent experiments suggest a tantalizing possibility. What if time doesn't flow uniformly at quantum scales? Hypothetical quantum clocks, particles whose internal states act as timekeepers, might tick at different rates even when placed in identical conditions, purely due to quantum uncertainty. It's as if each particle carries its own personal timeline, ignoring the synchronized cosmic clock we're accustomed to. One groundbreaking proposal comes from physicists studying quantum reference frames. They argue that in a quantum system, time could become relational, meaning it only has meaning when comparing one object's state to another's. Without this comparison, the very notion of time passing loses coherence. Imagine two entangled particles. If you measure one's spin, you instantly know its partner, no matter how far apart they are. Now apply that concept to time. Could entangled particles share not just states, but temporal experiences? Some models suggest yes, that quantum time dilation could allow particles to effectively borrow time from each other, creating localized pockets where causality itself becomes flexible. The implications are staggering. If time is indeed quantized at fundamental scales, it could explain long-standing puzzles like black hole information loss or the nature of the Big Bang. More pragmatically, quantum time effects might one day be harnessed for technologies like ultra-precise quantum clocks, where superposition allows multiple time measurements simultaneously. Already, experiments with supercooled atoms in optical lattices have shown hints of time behaving differently under quantum control, with atomic vibrations, nature's most precise metronomes, showing probabilistic rather than deterministic timing. Yet the greatest revelation might be philosophical. If quantum time dilation proves real, it would mean the universe has no master clock ticking steadily forward. Instead, time emerges from countless quantum interactions, a tapestry woven from trillions of tiny, uncertain threads. The next time you glance at a wristwatch, consider this. Its steady ticking is an illusion, a macroscopic average of microscopic chaos. Beneath the surface of reality, time may be as fluid and unpredictable as the quantum foam itself. And that changes everything. Binary star systems, where two stars locked in a gravitational dance orbit a common center, are nature's test labs for some of the most extreme time dilation effects in the universe. Picture two massive stars whirling around each other at blistering speeds, each one warping spacetime so intensely that time itself staggers under the strain. For astronomers, these cosmic duos aren't just celestial spectacles. They're precision instruments revealing how gravity twists time in ways that defy earthly intuition. Take the famous Taylor pulsar, a neutron star orbiting a companion so dense that its gravitational pull slows time by a measurable fraction, enough that over decades, the pulsar's rhythmic radio pulses arrive slightly offbeat, as if the universe itself is tapping its foot to a warped metronome. How do scientists actually detect these subtle time shifts? The secret lies in pulsars, rapidly spinning neutron stars that beam radio waves like cosmic lighthouses with atomic clock precision. When a pulsar orbits another massive object, its signals must climb out of a deep gravitational well, causing them to arrive at Earth slightly delayed compared to signals emitted farther from the star's grip. This delay, called the time delay, isn't just a theoretical curiosity. It's been measured to within a fraction of a percent in systems like the double pulsar J0737-3039. Each delayed pulse is a tiny cry from the depths of warped spacetime, whispering secrets about gravity's grip on time itself. But the real magic happens when these binary systems include a black hole. In 2020, astronomers observed a star orbiting Sagittarius A star, the supermassive black hole at our galaxy's center, and clocked its orbit at a staggering 15,000 miles per second, about 8% the speed of light. At those velocities, combined with the black hole's crushing gravity, time for the star slows dramatically compared to Earth's frame of reference. Over a single orbit, minutes pass differently for the star than for telescopes watching it, creating a natural relativity experiment on a galactic scale. These observations aren't just confirming, they're pushing his equations to their limits, probing regimes where unknown physics might lurk. What's truly astonishing is how these systems reveal the universe's hidden asymmetry. In most binaries, one star is more massive than the other, meaning time runs slower on its surface, a discrepancy that can add up to years over their lifetimes. Imagine two stellar siblings born at the same moment. The heavier one burns brighter but ages slower, its core processes stretched by relativity even as its lighter companion races ahead in time. This cosmic timekeeping quirk means massive stars might technically live longer from our perspective, their fusion furnaces throttled by their own gravity's time-slowing effect. The implications stretch far beyond stellar curiosities. Binary systems are proving grounds for technologies like LISA, the future space-based gravitational wave detector that will rely on time dilation measurements to pinpoint collisions between neutron stars and black holes across the cosmos. Every time we decode the time-warped signals from these dancing stars, we're not just studying distant suns, we're learning to read the universe's hidden clock, ticking unevenly in the shadows of gravity's strongest holds. And with each discovery, we edge closer to answering one of physics' biggest questions. In a universe where time is fluid, what does now even mean standing at the edge of a black hole? You'd face one of the universe's most baffling riddles. If time grinds to a halt at the event horizon, does anything ever truly fall in? From our perspective outside the black hole, an object approaching that boundary appears to freeze, its image into oblivion as time stretches into infinity. But here's the paradox: for the object itself, time flows normally. It would cross the horizon without drama, oblivious to the cosmic spectacle it leaves behind. This contradiction lies at the heart of a decades-long debate among physicists, splitting opinions on whether black holes are eternal prisons or cosmic shredders. The crux of the problem hinges on conflicting interpretations of relativity. The equations predict that, from an outsider's view, an object's descent asymptotically slows, never quite reaching the horizon within any finite time. Yet nothing in the theory prevents the object from experiencing a smooth passage inward. Both perspectives seem mathematically valid, creating a schism between what observers see and what actually happens. Some theorists argue this isn't just an illusion. It suggests black holes might never fully form in the first place, with collapsing matter eternally stuck just outside its own horizon. Others counter that the infinite time dilation is a quirk of coordinates, a mathematical artifact that vanishes if you switch reference frames. Enter quantum mechanics, which throws another wrench into the works. At the quantum level, particles can tunnel through barriers, meaning there's always a non-zero probability that something could bypass the horizon's time-frozen facade. This leads to wild proposals like firewalls, high-energy barriers at the horizon that shred incoming matter, or fuzzballs, where black holes are tangled knots of strings with no sharp boundary at all. The late Stephen Hawking even suggested that black holes might not have interiors in the traditional sense, with their contents smeared across the horizon in a quantum haze. The stakes couldn't be higher. If infinite time dilation is real, black holes might preserve information like cosmic fly amber, trapping snapshots of the universe's history forever. But if it's an illusion, that information could be lost or scrambled, violating quantum theory's sacred principle of reversibility. This isn't just academic. It could determine whether black holes are the universe's ultimate vaults or its most efficient shredders. Recent simulations using quantum gravity models hint at a middle ground. Some suggest the horizon acts like a turbulent quantum storm, where time fractures into probabilistic threads rather than stopping entirely. Others propose that time dilation peaks just before the horizon, creating a stretch zone where matter thins into spaghetti-like streams without fully freezing. These ideas remain speculative, but they underscore a profound truth. The paradox of infinite time dilation isn't just about black holes. It's a mirror reflecting our incomplete understanding of time itself. So where does that leave us? Until we reconcile relativity with quantum mechanics, the fate of objects crossing the horizon will remain one of physics' greatest enigmas. The next time you gaze at a telescopic image of a black hole's shadow, remember, you're not just looking at a cosmic vacuum. You're staring into a rift where time itself unravels and the universe's deepest secrets hide in plain sight. Dark matter has puzzled astronomers for decades, an invisible substance outweighing visible matter 5-to-1, yet refusing to interact with light or ordinary particles. But what if its elusiveness isn't just about what dark matter is, but how it experiences time? Enter one of relativity's wildest speculations, that dark matter's mysterious behavior could stem from extreme time dilation, warping its presence across the cosmos in ways we're only beginning to imagine. Picture a particle of dark matter drifting through a galaxy's halo. Unlike stars or gas, it doesn't collide or emit light, but here's the twist. Some theories suggest dark matter might cluster near regions of intense gravity, like black holes or galactic cores, where time slows dramatically. If these particles are subject to severe time dilation, their clocks could tick far slower than ours. A single dark matter interaction that takes a millisecond in its reference frame might span centuries and hours, making it seem inert when it's merely operating on a timescale we can't perceive. It's like watching a single frame of a movie and concluding nothing's happening. when in reality, the story's unfolding too slowly for us to see. This idea gains traction when you consider how dark matter behaves in galaxy collisions. Astronomers have observed clusters like the Bullet cluster, where dark matter, detected via gravitational lensing, seems to glide past normal matter without slowing down. If dark matter particles experience time differently, perhaps due to velocities near light speed or proximity to gravitational wells, their sluggish temporal flow could explain why they don't notice ordinary matter's presence. They'd be like commuters rushing through a train station, oblivious to the people moving in slow motion around them. The implications ripple deeper. If dark matter's time dilation varies across the cosmos, it could solve the corpuscle problem, the mismatch between predicted dense dark matter halos at galaxy centers and the smoother distributions we observe. Near a supermassive black hole, time dilation might stretch dark matter's dynamics over eons, preventing it from clumping as sharply as simulations suggest. This would mean our models aren't wrong. We've just been missing relativity's subtle fingerprints on dark matter's clock. Critics argue this theory stretches razor. Why invoke time dilation when simpler explanations exist? Yet proponents counter that dark matter's refusal to fit standard models demands unconventional thinking. After all, relativity once seemed equally radical before GPS proved its practicality. Future experiments could test the idea by searching for time-dependent anomalies in gravitational lensing, or studying how dark matter's distribution correlates with regions of extreme spacetime curvature. Whether this hypothesis holds or not, it underscores a profound truth. The universe's greatest mysteries might not lie in the particles we can't see, but in the time we don't share with them. Dark matter could be the ultimate cosmic stranger, not just passing through space, but drifting through time at a pace that renders it ghostly to our impatient eyes. And if that's the case, unlocking its secrets might require more than new telescopes. We might need to learn to read a clock that ticks in the shadows of relativity itself. Time dilation might not be a time machine, but it's the closest thing physics has to a roadmap for one. The idea of traveling backward through time has long been dismissed as fantasy, yet hidden in its equations are tantalizing clues that the universe might allow it under extreme conditions. Wormholes, those hypothetical tunnels through spacetime, could theoretically connect distant moments as easily as distant places. Picture a shortcut not just across space, but across centuries, where entering one end might deposit you in ancient Rome or a future colony on Mars. The catch: these cosmic gateways would require exotic matter with negative energy to stay open, a substance we've never observed but that quantum physics doesn't outright forbid. Then there's the even stranger concept of closed curves, paths through spacetime that loop back on themselves, allowing a traveler to return to their own past. In a universe with sufficiently warped geometry, perhaps near a rotating black hole or a cosmic string, these loops could exist without breaking relativity's rules. Imagine orbiting a massive, spinning black hole in just the right way. Your path through spacetime might twist into a circle, bringing you back to where and when you started. It's not magic, it's math. Physicists proved this mathematically in 1949, showing that equations permit timelines that bend into pretzels under the right conditions. But before you start drafting letters to your past self, consider the hurdles. Wormholes, if they exist, would likely be microscopic, unstable, and require energies beyond anything we can produce. Closed curves demand spacetime geometries so precise they might as well be cosmic Swiss watches. And then there's the infamous grandfather paradox. What happens if you accidentally prevent your own birth? Some theorists argue quantum mechanics could resolve this with parallel timelines, while others insist the universe would simply forbid such contradictions through some yet unknown law. Yet the mere possibility is revolutionary. Time dilation, once a curious side effect of relativity, becomes a stepping stone to even wilder ideas. The same physics that makes GPS satellites work also whispers that time might not be the one-way street we thought. Future civilizations, armed with technologies we can barely imagine, might view time travel the way we view air travel, not trivial but routine. Until then, every ticking clock is a reminder. The universe's rules are stranger than we dreamed, and the line between science and science fiction is thinner than it seems. The violent deaths of stars are more than just cosmic fireworks. They're time capsules, their light stretched and distorted by the universe's expansion in ways that let us peer billions of years into the past. When a massive star collapses into a supernova, the explosion doesn't just blast matter into space. It sends out a beacon whose journey through expanding spacetime carries secrets about time itself. Astronomers have observed distant supernovae whose light takes so long to reach us that their explosions appear to unfold in slow motion, their light waves stretched into lower frequencies, a phenomenon called cosmological time dilation. A supernova that should blaze for weeks in its own frame might appear to flicker for months from our vantage point, its timeline warped by the relentless stretching of the cosmos. This effect isn't just a curiosity, it's a critical tool for mapping cosmic history. The farther away a supernova is, the more its light is, and the more its apparent duration stretches. By comparing nearby supernovae, whose light arrives relatively undistorted, to their ancient counterparts billions of light years away, scientists can measure how the universe's expansion rate has changed over time. It's how we discovered dark energy in the late 1990s. Distant supernovae were dimmer than expected, proving the universe wasn't just expanding, it was accelerating. Those faint, time-dilated flashes were the universe whispering its deepest secret. Gamma-ray bursts take this to even greater extremes. These fleeting, hyperenergetic explosions, often caused by colliding neutron stars or collapsing stars, can outshine entire galaxies for mere seconds. Yet when we observe them across cosmic distances, their brief flickers stretch into lingering afterglows. A burst lasting 2 seconds in its home galaxy might appear to unfold over 20 seconds by the time it reaches Earth, its high-energy gamma rays smeared into lower-energy X-rays and visible light. This time dilation isn't just dramatic, it's computationally essential. Without accounting for it, astronomers would misjudge the true energy of these events, mistaking stretched, diluted light for intrinsically weaker emissions. But here, where it gets truly mind-bending. Some of these ancient explosions occurred when the universe was a fraction of its current size, meaning spacetime itself was more densely curved. The light from those events didn't just travel farther, it climbed out of a deeper gravitational well, adding gravitational time dilation to the cosmological kind. When we analyze a gamma-ray burst from 12 billion years ago, we're seeing an explosion that happened in a universe where time itself flowed differently, where the fabric of reality was younger, hotter, and more contorted. These aren't just distant fireworks, they're messages from an era when the rules of time were written in a different dialect. The next generation of telescopes, like the Observatory and the James Space Telescope, will push these observations even further. By catching supernovae and gamma-ray bursts from the universe's first billion years, a period known as cosmic dawn, we'll witness time dilation at its most extreme. These primordial explosions could reveal whether dark energy's strength has changed over cosmic history, or if unknown physics governed the early universe's expansion. Every stretched photon, every afterglow is more than data. It's a fragment of a story written in the warped language of relativity, waiting for us to decode it. And with each explosion we catalog, we're not just mapping space. We're reconstructing time itself, one dilated heartbeat at a time. Imagine an astronaut embarking on a mission at near-light speed. Their body would become a living laboratory for time dilation's strangest effects. While their ship's clock might show a 10-year journey, Earth could age centuries in the same span. But here's the catch. Relativity doesn't just warp time on a clock, it reshapes the very biology of the traveler. At extreme velocities, cellular processes, from metabolism to DNA repair, would slow relative to Earth, creating a paradox where the astronaut's body ages slower than the world they left behind. This isn't just theoretical. It's a physiological puzzle future interstellar explorers will face head-on. Take something as routine as cell division. On Earth, human cells replicate roughly every 24 hours, a rhythm governed by molecular clocks. But aboard a ship moving at 80% light speed, time dilation would stretch that cycle to nearly 40 hours from Earth's perspective. The astronaut's body would effectively underage, their cells dividing fewer times over the mission compared to their peers back home. This could delay visible aging, wrinkles, gray hair, muscle loss, but it might also disrupt systems reliant on precise timing, like immune responses or wound healing. A minor injury that normally heals in days could persist for weeks in ship time, complicating long-duration missions. Then there's radiation, a silent threat by relativity. Cosmic rays bombard spacecraft at high energies, and time dilation would alter how astronauts experience that exposure. While their subjective years in transit might feel brief, the cumulative radiation dose could be far higher than Earth-based calculations predict. Picture this: a particle that would typically pass harmlessly through a stationary body might, due to relativistic effects, deposit catastrophic energy in a fast-moving traveler's tissues. Shielding that works perfectly on Earth might fail under these distorted conditions, turning a routine solar flare into a lethal event. But the quirks don't stop there. Consider circadian rhythms, the internal clocks keeping us alert by day and sleepy by night. On a relativistic journey, the absence of a 24-hour light-dark cycle, combined with time dilation, could desynchronize these rhythms entirely. Astronauts might battle chronic jet lag as their biological clocks tick out of sync with both mission schedules and Earth time. Even artificial lighting calibrated to mimic Earth's day might prove futile when time itself flows differently. The result? A crew trapped in a twilight of fatigue, their bodies perpetually out of phase with their environment. Perhaps the most unsettling question is how the brain would cope. Human memory and cognition rely on neural firing patterns that could slow under extreme time dilation. Would astronauts think and react at normal speed, or would their perception of time stretch like molasses? Studies on high-speed particles suggest cognitive processes might remain consistent from the traveler's perspective, but Earth-bound observers could perceive their reactions as sluggish. Communication delays, already a challenge in space, would become insurmountable. A simple exchange with mission control could take years, rendering real-time dialogue impossible. The ultimate irony: returning astronauts might find their bodies biologically younger than their own children. Families reunited after a brief mission could face emotional whiplash, with parents outliving generations of descendants. This isn't just a biological curiosity, it's an ethical dilemma. How do we prepare explorers for the psychological toll of outliving everyone they love? Science fiction often glosses over this toll, but real-world relativistic travel would force us to confront grief on a scale we've never imagined. Medical science offers no easy answers yet, but research is. Experiments with particle accelerators and atomic clocks hint at how organic molecules behave at relativistic speeds. Meanwhile, studies on astronauts aboard the ISS, where time dilation, though minuscule, still exists, provide baseline data on aging in microgravity. The path forward might lie in biotechnology, engineered cells with radiation-resistant DNA, or drugs that stabilize circadian rhythms independent of external time cues. One day, we may even develop time-aware medicines that adjust their release rates based on the body's relativistic state. The human body wasn't designed for time dilation, but neither was it designed for yet here we are. As we push toward the stars, we'll need to reimagine not just spacecraft, but the very flesh and blood inside them. The astronauts who brave these journeys won't just be explorers, they'll be pioneers of a new kind of humanity, one that bends time's rules to survive them. And when they step onto distant worlds, they'll carry with them not just the legacy of Earth, but the paradox of having lived outside its time. If alien civilizations exist, they've likely mastered time dilation, not as a curiosity, but as the foundation of their technology. Picture a species millions of years ahead of us, for whom relativity isn't a theory but a tool as mundane as electricity is to us. Their interstellar ships might ride the edge of black holes, using gravitational time dilation to make centuries pass in weeks, turning galactic exploration into a single lifetime's work. Communication could rely on precisely timed pulses stretched by relativity, allowing messages to cross light years without losing coherence. The very structure of their societies might revolve around temporal engineering, with different factions experiencing time at radically different rates, some living in accelerated bubbles to outpace rivals, others hibernating in slowed spacetime to await cosmic events. This isn't just speculation, it's grounded in the Fermi paradox's unspoken assumption. If the universe is so vast and ancient, where is everyone? One unsettling answer: they're everywhere, but operating on timescales we can't perceive. Advanced civilizations might communicate or travel in ways that leverage time dilation, making their signals or ships invisible to our primitive detectors. Imagine an alien probe passing through our solar system at 99% light speed. From its perspective, the journey takes days, but to us, it's a blur lasting microseconds. We wouldn't just miss it, we'd lack the technology to notice time itself bending around it. Consider the implications for SETI, the search for extraterrestrial intelligence. Traditional scans look for radio waves or laser pulses, assuming aliens communicate in real time. But what if their messages are stretched or compressed by relativity? A single transmission could arrive as a years-long whisper, its content smeared across time like a record played at the wrong speed. Decoding it would require not just linguistic skill, but an understanding of the sender's relative velocity or gravitational environment. Even their artifacts might be temporally cloaked. A sphere built near a neutron star could experience such extreme time dilation that its construction appears frozen to outside observers, disguised as a natural phenomenon. The darkest twist: time dilation might explain why advanced civilizations avoid contact. Species that harness relativity could view unaltered as primitive, even dangerous. To them, we might be like mayflies, our lives so brief that meaningful interaction is impossible. Or worse, they could see us as temporal pollution, our unchecked expansion risking disruptions to carefully calibrated cosmic timelines. The universe's greatest filter might not be extinction, but the inevitability that intelligence evolves beyond shared time. Yet there's hope. If aliens do manipulate time dilation, their signatures might lurk in anomalies we're already detecting. Fast radio bursts, those mysterious cosmic flashes, could be relativistic data packets, their frequencies distorted by near-light speed travel. Unexplained gaps in stellar motion might mark the passage of time-bent spacecraft. Even dark matter's odd behavior might hint at civilizations dwelling in extreme gravitational fields, their very atoms ticking slower than the rest of the universe. The key to finding aliens may lie not in scanning space, but in decoding time's hidden wrinkles, where the future, past, and distant present collide. What if our universe isn't the only one where time bends? Imagine a future where we create hyper-realistic simulations, entire digital worlds with their own laws of physics. Now here's the mind-bending question. Would time inside those simulations run slower than time outside? This isn't just science fiction. It's a real philosophical and computational puzzle with implications that could redefine our understanding of reality. If we ever build virtual universes complex enough to mimic our own, their very existence might depend on how time dilation manifests in code. Think about the computational cost of simulating time itself. Every second in a virtual world requires processing power. The more detailed the simulation, the more resources it consumes. To save computing capacity, engineers might intentionally slow down time within the simulation relative to the outside world. A single minute of real-world processing could equate to hours or even years of simulated time, creating a form of digital time dilation. This isn't hypothetical. We already see glimpses of it in rudimentary forms. Video game engines often use time scaling to prioritize rendering efficiency, where non-critical elements update less frequently than the player's immediate environment. Scale that up to a universe-sized simulation, and you've got a temporal hierarchy where different layers of reality tick at different speeds. But the implications go far beyond processing shortcuts. If simulated beings inside one of these worlds develop consciousness, their entire experience of time would be dictated by the simulation's architecture. A civilization rising and falling in what feels like to them might unfold in mere days for the operators outside. This raises eerie philosophical questions. If time is fluid in simulations, could our own universe be nested inside a larger system where time flows differently? Some theorists argue that if simulations are possible, the statistical likelihood we're in the base, reality dwindles, meaning our perception of time might already be an artificial construct. Then there's the hardware problem. Even with quantum computers, simulating every particle in a universe at real-time speed seems implausible. But if time inside the simulation runs orders of magnitude slower, the task becomes feasible. Imagine a supercomputer calculating a single simulated second over the course of an external hour. Suddenly, creating a billion-year cosmic history takes only a fraction of that in the real world. This isn't just about efficiency, it's about making the impossible possible. Digital time dilation could be the key to unlocking universe-level simulations without infinite resources. The most unsettling possibility, if we're in a simulation ourselves, the glitches we can't explain, quantum indeterminacy, dark energy, even might be artifacts of an external system optimizing its processing. Time dilation could be the simulation's way of balancing its computational load, slowing down complex calculations in certain sectors while speeding up simpler ones. The next time your computer freezes for a second, consider this. Our universe might be someone else's lagging processor, struggling to render reality in real time. Time dilation doesn't just bend physics, it twists the very fabric of human relationships and societal structures. Imagine a crew of astronauts returning from a decades-long mission near a black hole, stepping onto an Earth where centuries have passed. The world they knew is gone, replaced by a civilization that moved on without them. Their families are long dead, their cultures transformed beyond recognition, and their skills, once cutting-edge, are now archaic relics. This isn't just a logistical challenge, it's an ethical minefield. How do we reintegrate travelers who are, in every practical sense, refugees from the past? Who bears responsibility for their psychological well-being when their grief spans generations they never got to witness? The legal implications alone are staggering. Consider property rights. If a traveler left behind assets or intellectual property, do their descendants now own them? What about contracts or marriages? Are they void after a century of separation? Legal systems assume a shared timeline, but relativity shatters that premise. A colonist who signs a 50-year lease on Mars might return to find Earth's courts have dissolved it ago due to abandonment. even citizenship becomes murky. Does someone born in the 21st century retain rights in a 25th century polity that no longer recognizes their nation's existence? These aren't hypotheticals, they're inevitabilities if relativistic travel becomes routine. Then there's the question of cultural contamination. Time-dilated travelers carry archaic languages, customs, and beliefs, precious to anthropologists but potentially disruptive to a future society. Imagine a crew from our era arriving in a post-climate crisis world where water scarcity reshaped morality. Their casual wastefulness, harmless in their original context, could offend or even endanger their hosts. Conversely, future humans might view returnees as living museums, pressuring them to perform there for entertainment or profit. The ethical tightrope is clear. How do we protect travelers from exploitation while respecting the autonomy of the future they've joined? Perhaps the most haunting dilemma is consent. Current space missions require informed consent for risks, but how do you consent to losing everyone you love? No waiver can prepare someone for the reality of outliving their children or returning to a world where their life's work is irrelevant. Should we even permit such missions, knowing the emotional toll? Some ethicists argue that relativistic travel is inherently coercive, as no one can truly grasp the psychological weight of time dilation until it's too late. Others counter that exploration has always demanded sacrifice, and stifling it over hypothetical suffering is cowardice. The debate mirrors historic clashes over colonization and Arctic expeditions, but with stakes by relativity's uncaring math. Underlying all this is a deeper question. Does humanity have a duty to preserve continuity across time? If we scatter colonies across the galaxy, each evolving at different relativistic rates, we risk fracturing into disconnected subspecies, not just biologically, but temporally. A civilization that masters time dilation might eventually shatter into parallel societies unable to coexist, their clocks desynchronized not by minutes, but by epochs. The same physics that enables interstellar travel could doom us to cosmic isolation. Our shared history stretched thin across the infinite gradients of warped spacetime. Yet for all these challenges, time dilation also offers a paradoxical gift, the chance to witness humanity's long arc firsthand. A single observer hopping between relativistic journeys could watch civilizations rise and fall like seasons, becoming a living bridge between eras. Their perspective, unique in all of history, might hold the key to solving problems that span centuries, from climate change to existential risks. The ethical dilemmas are immense, but so are the opportunities. The choice isn't whether to face these questions, but how soon we're willing to start answering them. Long before scribbled his first equations about relativity, ancient cultures were already wrestling with the idea that time could flow differently in different realms. Take the Hindu epic Mahabharata, where king returns from a brief visit to the celestial realm of Brahma, only to find that thousands of years have passed on Earth. His entire civilization vanished, his family long dead. Or the Japanese legend of Taro, a fisherman who spends what feels like days in an undersea palace, only to emerge centuries later, his village reduced to ruins. These aren't just poetic flourishes, they're uncanny echoes of time dilation, as if our ancestors glimpsed the warping of spacetime through the lens of myth. The parallels grow even more striking when you examine Abrahamic traditions. A verse describes how a day with your Lord is like 1,000 years of what you count, a line that takes on new meaning when you consider how gravity near a massive object could stretch seconds into. Even the biblical story of Elijah, who ascends to heaven in a whirlwind and returns centuries later in Jewish folklore, mirrors the twin paradox, where a traveler's journey warps their place in history. These stories span continents and eras, yet they share a common thread. The understanding that time isn't fixed, that divine or otherworldly realms operate on clocks beyond human comprehension. What's fascinating is how these myths often tie distorted time to extreme environments, mountain tops, deep waters, celestial kingdoms, places later physics would recognize as gravitational or velocity-based time dilation hotspots. The Buddhist tale of the monk, who meditated in a cave only to emerge into a future where his temple had crumbled, finds a bizarre counterpart in modern experiments with atomic clocks in caves versus mountains. The deeper the gravitational well, the slower time crawls, a fact our ancestors seem to intuit through metaphor. Skeptics might dismiss these connections as coincidence, but consider this. Indigenous Australian Dreamtime stories describe ancestral beings moving between worlds where time stands still, a concept eerily similar to the frozen clocks at a black hole's event horizon. The Maori of New Zealand speak of Po, the timeless void before creation, where existence was, without years, a phrase that could double as a description of the singularity before the Big Bang. These cultures had no telescopes or particle accelerators, yet their narratives resonate with relativistic principles in ways that defy simple chance. The real mystery isn't whether ancient people understood relativity. They clearly didn't in the scientific sense, but why so many disparate civilizations embedded time-warping motifs into their foundational stories. Perhaps it's humanity's collective subconscious recognizing that time is more fluid than it seems. Or maybe these tales preserve half-remembered encounters with natural phenomena, like meteor showers or eclipses, that momentarily shattered their perception of time's flow. Whatever the origin, these myths challenge our arrogance as modern thinkers. They suggest that the universe's secrets don't always reveal themselves through equations first. Sometimes, they whisper through stories, waiting centuries for science to catch up. Today, as physicists probe quantum gravity and multiverse theories, we're left to wonder, will future generations look back at our current myths, our sci-fi films, and theoretical thought experiments as prophetic glimpses of truths not yet formalized? The line between ancient wisdom and cutting-edge science may be thinner than we think, woven together by the timeless human instinct to question how deep time's rabbit hole really goes. What if time dilation isn't just bending the rules of reality? What if it's exposing time itself as a cosmic mirage? Beneath the equations and experiments, a radical idea is gaining traction among physicists. That time isn't fundamental at all, but an illusion emerging from something deeper. Think of it like temperature, a useful concept that feels real, but ultimately arises from the chaotic dance of countless molecules. Could time work the same way, with dilation acting as a clue that we're seeing the seams of a universe stitched together without time as its fabric? This perspective flips everything we know about relativity on its head. Instead of time being a dimension that warps under gravity and motion, it might be a collective hallucination born from quantum entanglement, the mysterious link between particles that defies classical physics. Picture two entangled electrons. When one spin is measured, the other instantly mirrors it, no matter the distance. Now imagine this happening trillions of times across the universe, creating a web of correlations so dense that our brains interpret it as a flowing timeline. Time dilation, in this view, wouldn't be about stretching moments. It would reveal where the illusion frays, like a glitch in the matrix. The evidence lies in black holes, those cosmic shredders where time appears to freeze at the event horizon. From our vantage point, a falling object never quite crosses the boundary, its image eternally stuck in slow motion. But if time is emergent, this infinite stretching might be a signpost pointing to its breakdown. Just as water loses its wetness, when you zoom into individual H2O molecules, time could dissolve into something more primitive near a black hole's extreme gravity. Quantum gravity theories like loop quantum relativity take this further, proposing that spacetime is pixelated at the tiniest scales, with time emerging from these discrete building blocks like a movie from individual frames. Here, where it gets even stranger, If time is illusory, then the past, present, and future might all exist simultaneously, a concept called the block universe, where dilation is just our limited perspective on a static four-dimensional structure. Your childhood, this moment, and your distant future would all be equally real, with time's flow being a trick of consciousness. This isn't just philosophy, it's testable. Experiments with quantum clocks are now probing whether time emerges from entanglement, with early results suggesting entangled particles can synchronize their ticks in ways that defy classical timekeeping. The implications are dizzying. If time dilation reveals time's emergent nature, then aging, cause and effect, even memory might be secondary phenomena, side effects of a deeper order we're only beginning to glimpse. Future technologies might not just manipulate time's flow, but bypass it entirely, using quantum correlations to store information outside the arrow of time. Cultures that mythologized timeless realms might have been closer to the truth than they knew. The universe, it seems, is playing the ultimate sleight of hand, convincing us time is real while hiding the cards up its sleeve. What if the time dilation we observe in our universe is just a shadow of something far stranger happening in dimensions we can't perceive? String theory, the bold framework that unites quantum mechanics and relativity, suggests our reality might be floating in a cosmos with 10 or more dimensions, most of them curled up so tightly we'd never notice. But here's the twist. If these extra dimensions exist, they could harbor forms of time dilation that make black holes look tame. Picture a universe where time doesn't just slow down near massive objects, it fractures entirely, branching into flows that defy our three-dimensional intuition. Take the concept of brane worlds, a radical idea from string theory where our entire universe is a three-dimensional membrane drifting through a higher dimensional space. If another brane universe passed near ours, its gravity could leak through the extra dimensions, warping time in ways that would appear magical to us. Clocks might suddenly speed up or slow down without any visible cause, as if reality itself were glitching. Astronomers have even scanned the cosmos for signs of these phantom gravitational tugs, anomalies in supernova brightness or galaxy rotations that hint at unseen dimensions twisting spacetime behind the scenes. Then there's the multiverse hypothesis, which suggests every quantum decision spawns alternate timelines. In this mosaic of realities, time dilation could operate differently in each universe, depending on their unique physical constants. One universe might have time flowing like molasses, where civilizations rise and fall in what we perceive as minutes. Another could be a frenetic blur, with stars forming and dying in microseconds. If higher dimensions connect these worlds, travelers crossing between them might experience time shifts so extreme they'd lose all connection to their original timeline. The real enigma lies in how we detect these effects. While our instruments measure time dilation through, or atomic clocks, higher dimensional time warps might leave subtler fingerprints, perhaps as statistical anomalies in particle collisions at CERN, or as unexplained lags in quantum entanglement experiments. Some theorists propose that dark energy itself could be a signature of time leaking into extra dimensions, a cosmic pressure stretching our universe while other branes experience time at entirely different rates. Yet the most mind-bending possibility is that we're already experiencing higher dimensional time dilation without realizing it. Dreams, or even the subjective feeling that time speeds up as we age, might be glimpses of dimensions where time operates beyond linear flow. Ancient cultures spoke of sacred spaces where time stood still. Could these be folk memories of rare moments when the veils between dimensions thinned? Whether these ideas hold up or not, they push us to rethink time's nature. If alternate dimensions exist, then time dilation isn't just a quirk of our universe. It's a multilingual phenomenon, speaking in dialects we've yet to decipher. And somewhere beyond our perception, clocks may be ticking to rhythms we can't yet hear. The dream of bending time to our will is no longer confined to science fiction. Cutting-edge research is already laying the groundwork for technologies that could harness time dilation as routinely as we harness electricity. Imagine a spacecraft equipped with a warp bubble, not to break light speed, but to manipulate the flow of time around it. Recent experiments with metamaterials, synthetic structures engineered to bend light in unnatural ways, hint that we might one day create time lenses capable of compressing or stretching temporal intervals on demand. These wouldn't be portals to the past, but tools to control how quickly events unfold within a localized area. Picture a medical pod where a surgeon could slow a patient's biological clock during complex operations, buying precious minutes when every second counts. Or a disaster response team using temporal compression to analyze crises in what feels like hours, while the outside world experiences mere seconds. The most tantalizing possibility lies in propulsion. NASA's lab has explored theoretical designs for drive, a concept inspired by relativity that would contract spacetime in front of a ship while expanding it behind, effectively surfing a wave of warped time. While the energy requirements are currently beyond our reach, breakthroughs in quantum vacuum engineering or dark matter manipulation could change that. Such a drive wouldn't just shorten travel time, it would sidestep it entirely by creating a pocket where time flows differently for travelers than for the universe at large. A trip to Alpha might take 4 years on Earth's clocks, but only weeks for the crew inside the bubble. This isn't just about speed. It's about redefining what now means across interstellar distances. But time manipulation could reach even further into daily life. Quantum clocks synchronized across global networks might one day enable temporal GPS, allowing devices to account for microscopic time dilation caused by altitude, velocity, or even the density of nearby buildings. Financial markets could timestamp transactions with precision immune to relativistic drifts, while power grids might use time lensing to stagger energy flows across nanoseconds, eliminating bottlenecks. The military already studies temporal cloaking, briefly bending light to create gaps in detection systems, and civilian applications could follow, like cameras that capture processes by slowing their perception of time. The ethical dilemmas are as vast as the potential. Would time-manipulating technologies widen inequality if only the wealthy could afford to buy extra moments? How do we legislate crimes committed across dilated timelines, where a suspect's alibi depends on their frame of reference? And what happens to cultural continuity if some communities choose to live at half speed while others accelerate? These questions sound like Black Mirror episodes, but they're logical extensions of physics we already know to be true. Perhaps the most profound implication is artistic. If we master time dilation, storytelling itself could transform. Films might offer viewer-adjustable pacing, where you experience key scenes in slow motion while secondary events flash by. Virtual reality could simulate centuries of civilization growth in an afternoon, or stretch a single sunset into a meditative week. Musicians might compose where each instrument exists in its own temporal stream, harmonizing across dimensions of time. The very fabric of human expression could become fluid, unshackled from the tyranny of the universe's clock. We're standing at the threshold of a revolution far stranger than the invention of clocks or calendars. For time was the one force humanity couldn't tame. But relativity whispers that the stopwatch of the cosmos has always been adjustable. The technologies we've imagined here may take centuries to realize, or they might emerge next decade from a lab we've never heard of. One thing is certain, the future belongs to those who understand that time isn't a river sweeping us helplessly along. It's an ocean and we're learning to swim. Time dilation has taken us on a journey through black holes, speeding spaceships, and even the fabric of reality. But now we arrive at the most unsettling question of all. Is time itself just an illusion? Every example we've explored, from atomic clocks on airplanes to astronauts aging slower, points to a universe where time is fluid, malleable, and deeply personal. But what if these phenomena aren't just bending time? What if they're revealing that time, as we understand it, doesn't fundamentally exist? This isn't just philosophy, it's a frontier where physics and metaphysics collide. Consider temperature, a concept that feels undeniably real until you zoom in and realize it's just the average motion of countless molecules. Time might operate the same way, an emergent property of something deeper, like quantum entanglement or the way particles interact across spacetime. Think of a movie projected on a screen. The illusion of motion comes from static frames flashing by quickly. Could our perception of time be similarly constructed, with dilation acting like a glitch in the projector, exposing the individual frames beneath? Experiments with entangled particles already show that quantum systems can synchronize without any obvious timekeeping, hinting that what we call time might just be a side effect of these invisible connections. Even hinted at this radical idea. His equations treat time as a dimension, but they also allow for solutions where cause and effect blur, like closed curves where events loop back on themselves. Some physicists argue this flexibility suggests time isn't a primary ingredient of the universe, but a shorthand for relationships between objects. Picture a cosmic game of dominoes. We perceive a sequence of falls as time, but the dominoes themselves don't care about the order, they just exist. In this view, time dilation isn't about stretching moments. It's about revealing where the dominoes are spaced unevenly, creating the illusion of faster or slower progression. The implications are staggering. If time is emergent, then the past, present, and future might all exist simultaneously, a block universe where every moment is equally real, and our sense of flow is just how consciousness navigates this structure. Dilation would then be a quirk of perspective, like how a mountain appears small from a plane but towers over you up close. This could explain why quantum particles seem to know things instantaneously across distances. They're not breaking time's rules, they're operating outside them entirely. But the most profound clue lies in black holes. At the event horizon, time appears to freeze from an outsider's view, yet anything crossing it feels no sudden stop. This paradox might not be a flaw in relativity, but a signpost. Just as water loses its wetness when you isolate a single molecule, time might dissolve into something more fundamental near these extremes. Theories like loop quantum gravity propose that spacetime is pixelated at tiny scales, with time emerging from discrete interactions, like a digital video rendered frame by frame. So where does this leave us? If time is an illusion, then aging, memories, even history itself are stories we tell to make sense of a timeless reality. The next time you check your watch, remember, it might not be measuring something universal, just your place in a vast, unchanging tapestry where now is as fluid as your motion through space. The universe doesn't keep time, it weaves it. And in that weaving, the deepest mystery of all awaits. If time isn't real, what else might we be missing from the mind-bending twin paradox to the infinite time freeze at a black hole's edge? These 24 predictions peel back the layers of our universe's greatest illusion, time itself. What began as radical thought experiment has blossomed into a century of revelations, proving that time isn't a steady drumbeat but a symphony of warps and bends, playing at different tempos across the cosmos. Whether you're a sci-fi lover marveling at Interstellar's accuracy or a physics buff pondering quantum clocks, these ideas do more than challenge textbooks. They rewrite our very sense of reality. Consider the everyday miracles we now take for granted. GPS satellites correcting for microseconds of time dilation, or particle accelerators stretching subatomic lifetimes through sheer speed. These aren't just technological triumphs. They're proof that relativity isn't confined to the far reaches of space. It's woven into the fabric of our lives, hiding in plain sight every time your phone maps a route or a muon survives its impossible journey to Earth's surface. The universe whispers its secrets through these phenomena, inviting us to listen closer. Yet for all we've uncovered, the biggest mysteries remain. Is time truly fundamental or just a shadow of deeper quantum connections? Could aliens harness dilation in ways we've yet to imagine? And if we ever master temporal engineering, what will it mean to be human when our stretch across centuries or contract into fleeting moments? These questions linger at the edge of science, blurring the line between what we know and what we dare to dream. If this journey through the untold consequences of time dilation left your head spinning, you're not alone. The universe has a way of appending our assumptions, reminding us that wonder is the first step toward discovery. So hit like if you're ready to question everything, subscribe for more deep dives into the cosmos, best-kept secrets, and drop a comment below what prediction blew your mind the most. Until our next adventure, keep gazing at the stars and pondering the unthinkable. After all, as relativity shows us, the next great revelation might be hiding in the very